Now let's consider the steps for designing a resonant wireless power transfer system. So what will be given for us is basically the DC voltage of the transmitter side that's available. What is the DC load resistance that we need to power, or this wireless power transfer system is used to power? And what is the resonant frequency? And typically it's 6.78 megahertz for a resonant wireless power transfer system. Okay. And then we will also have information about the channel, or essentially the coupled inductors. All you need to do, or what will be given, just the self-inductance of the primary side, secondary side, and the coupling factor, essentially K. And from that, if we look at what we need to design, if we look at the secondary side, or essentially the receiving side, we need to determine the value of C2 and its ratings, basically the RMS current rating, the maximum RMS current that C2 can handle, as well as the maximum voltage across its terminals. And once we know its value as well as its ratings, we can go to any online supplier and order this component, the component that satisfies these ratings as well as the value. And the other component is basically the diodes. We need to know essentially what is the forward voltage drop that's required for these diodes, and what are the maximum ratings, basically the maximum DC current in these diodes. When we order these diodes online, we should make sure the diodes that we order will be able to handle this maximum DC current component, and what will be the maximum voltage, reverse voltage across these diodes, as we're going to discuss in detail in a few slides. And finally, of course, we need to select the output decoupling capacitor depending on the load, if it's a battery or it's just a pure resistive load. And in this case, we can follow a similar approach to how we calculated the output decoupling capacitance for a power supply. Now, for the transmitter side, we need to determine the value of C1 and its RMS current rating and maximum voltage rating, as well as we need to determine the switch's equivalent on resistance that we need, as well as the maximum voltage and maximum current. And we already did this in the first or in parts 1 and 2 of the wireless power transfer system videos. So now let's look at the receiver and how to determine the values. C2 already we mentioned that is determined by, we need to resonate with the secondary side inductance L2 at the resonant frequency F node. So basically we determine C2 from the equation. C2 is equal to 1 over omega node square times L2. Now, how we determine its ratings? And basically here we need to also make sure that the RMS current rating for both the capacitor C2 and the secondary side inductor are not exceeded. Here I'm assuming that we already given the, like we are not designing the transmitting and receiving coil, rather we are given the parameters already, or we take these primary and secondary coils from a supplier. But we just need to make sure that the RMS current that's flowing in the inductor L2, the secondary side, as well as the capacitor C2, doesn't exceed essentially the rating, the maximum RMS current of the inductor or the secondary coil, as well as C2. So the question here is we need to find the RMS current on the secondary side. Okay, so how can we do this? Well, if we calculate the output power, the power that is delivered to the load somehow, we know that this output power, since we're going to see the equivalent input resistance of the rectifier, this output power can be equal to, or can be expressed as IRMS secondary side squared times Rn. So how to find the value of the output power? Well, the output power, we can say it will be the input power, the power taken from the input, which we calculated in a prior video, times the efficiency of the primary side or the transmitter, times the efficiency of the receiver or the secondary side. Okay, so what is the efficiency of the secondary side, for example? Well, the efficiency of the secondary side, assuming high quality factor for the secondary side, for the RL, for the LCR circuit essentially, is going to be equal to the load resistance, the AC load resistance, which is the equivalent input resistance looking into the bridge rectifier, Rn. That's the useful resistance that delivers, that represents the power that's delivered to the output load, so the useful power, divided by Rn plus R2, where R2 essentially represent the equivalent series resistance of the secondary coil, so R2, plus the equivalent series resistance of C2, in addition to any equivalent resistance for the diodes themselves. So we know that when a diode conducts, essentially it can be represented as a resistor, R small d, and there is a forward voltage drop, for example, like in this way, Vd, where this is the anode terminal and this is the cathode terminal of the diode. Okay, so this is R2, and this essentially represent the efficiency of the secondary side, which is basically the power that's delivered to the load, Rn in this case, divided by the total power that's delivered to the receiving side or the secondary side of the transformer. Now, what about the efficiency of the primary side? We said the output power will be the input power multiplied by the efficiency of the transmitter times the efficiency of the receiver or secondary side. What about the efficiency of the primary side or the transmitter? Well, as we mentioned, essentially the transmitter can be modeled by this simple circuit. And so, as we know, there will be an equivalent on resistance R1 that's equal to the equivalent series resistance of the primary side, which is R1, plus the equivalent series resistance of the capacitor RC2, plus R31, sorry, plus the equivalent on resistance of the switches S1 or S2, essentially, as we did before, which is equal to RDS. Now, the efficiency will be the power, useful power, that is delivered to Ri, where Ri is equal by this expression as we discussed in the previous video. So essentially the efficiency of the primary will equal to the power that's delivered to Ri, the useful resistance, divided by Ri plus R1. And so by calculating the efficiency of the transmitter, the efficiency of the receiver, and we already calculated the input power before, then we can multiply them together, we get the output power. So what are we going to do with the output power? Well, what we're looking for is the RMS current, maximum RMS current that's flowing in the secondary side as well as the capacitor, in order to determine the RMS current rating that's required for the capacitor and secondary side coil of the transformer or coupled inductors. And in this case, it's very simple. The RMS current, if we know that the output power is equal to, here we see Rn, and here the RMS current is IRMS secondary. It will be the IRMS in the secondary squared times Rn. And so the value of the RMS current in the secondary is equal to the output power divided by the equivalent input resistance of the full bridge rectifier, square root. And that's it. Now we found the RMS current rating, or the maximum RMS current that will flow in the capacitor as well as in the secondary side coil. And so when we order a component, the capacitor specifically in this case, because I'm assuming we already have the transmitting and receiving coil as given in the problem, then when we order the capacitor, essentially we should make sure its current rating, RMS current rating, must be higher than this value that we just calculated. The second rating for the capacitor is the maximum voltage that's across the capacitor. And that's simple to calculate. Essentially, we already found the RMS current in the secondary side. If we multiply that by square root 2 and assuming high quality factor for the secondary side RLC circuit, then essentially the peak value will be basically square root 2 times RMS current, because in this case the current in the secondary is a pure sine function, and the peak value is basically given by square root 2 times RMS value that we just calculated. And so to get the voltage across the capacitor, we should multiply this current, peak current, times its reactance. And so if we just interested in maximum or the amplitude of the voltage across the capacitor, we don't need to include the J. So the maximum voltage across the capacitor C2, max, the amplitude essentially, will be that RMS current multiplied by square root 2 multiplied by 1 over omega naught C2. And that will be the maximum voltage across the capacitor. So now we know the value of C2. We know the value of the RMS current rating, it's a required RMS current rating, as well as the maximum voltage across its terminals. Now let's look at how we design the diodes. If we look at the data sheet of any diode, we'll find there are three important parameters or ratings that we need to take care of. The first one is the forward voltage. So when the diode conducts, essentially, we'll find that it can be represented by an ideal battery in series with an equivalent on resistance. This is essentially the forward voltage drop that's given in the data sheet. And this will be the diode equivalent on resistance, which you can also find it from the data sheet. Now, the ratings that we need to be careful about, or when we order a diode online from a supplier, we should make sure that diode we order is able to handle these ratings. There are two ratings. The first one is the maximum voltage across the diode, which is called typically in the datasheet peak repetitive reverse voltage, because basically the datasheet assumes the diode is used in a periodic circuit. And the second one is a diode maximum DC current, or what's called average forward rectified current. So it's basically the maximum DC component in the rectified current that the diode can handle. So if we look at the diode say conducts half a sine and then it turns off half sine. So what will be this DC component? Then we need to make sure that the diode from the data sheet that the average forward rectified current must be larger than this value of our design. Otherwise, the diode is going to burn, essentially cannot handle that maximum current, DC current. So first, let's see how we calculate the peak reverse voltage across the diode. Well, say when, as I discussed in a previous video, say when D0 and D2 are on in the negative half cycle, we'll see that the maximum voltage that's across essentially say D3 will be what? Reverse voltage. So D3 and D1 will be open circuit, of course, while D2 and D0 are on. So basically the maximum voltage across D3 will be, reverse voltage will be essentially VDC itself. However, if we consider the fact that when a diode turns on, it behaves as a battery basically, and we ignore the voltage drop across the equivalent on resistance of the diode. So we have V forward here, or VD, whichever which one you like to call. So basically the maximum reverse voltage across the diode will be the addition of VDC plus VF. Or essentially it's the DC output voltage plus one diode voltage drop. Now the question is, what is the value of VDC? Well, we already calculated the output power as the input power multiplied by the efficiency of the transmitter times the efficiency of the receiver. So this output power is what? Will be VDC square. Here we are approximating, this is approximately an expression because essentially this diode will cause some losses. But typically one thing we select for this diode to make sure that their losses are minimal is that we select them such that their forward voltage is less than the DC voltage divided by 10, so 1/10. So essentially we can ignore the losses in these diodes. for simplicity. So P out will be VDC square divided by the DC load resistance R. In this case, we are ignoring the power losses, conduction losses that happens in these diodes. And the reason is we select the diodes by design. The diodes we select, they have a forward voltage that's less than 1/10 of the DC output voltage. Now, once we get this expression, so we can find the value of VDC as output power multiplied by the DC load resistance square root. And from that value, we can find the maximum voltage across any of the diodes. Vmax, required maximum voltage rating, is VDC plus V for 1 forward voltage drop. Okay, so that's the first rating for the diode. The second rating is what is the DC current that will flow in the diode, and therefore when we select a diode online, we should make sure that the rating of that diode exceed the DC current that our design will see, or the diode in our design will see. Well, we mentioned before the current that's flowing I2 here is shown as this black sinusoid waveform. And this black sinusoid has an amplitude value that's equal to the RMS value that we calculated multiplied by square root 2, where the RMS current is, as we calculated before, from the output the output power as square root R out, P out. Let me write it cleaner. The amplitude of this sine function, which is basically I2, is going to be square root 2I RMS 2, and IRMS 2 is equal to the square root of P out divided by Rn, as we did a few slides ago. And we discussed before that this LC tank behaves as a current source, so D1 and D2, D1 and 3 will be on during the first half cycle, while D2 and D0, the even number diodes, will be on during the second half cycle, which flips the current with respect to the DC load. So the current here is always the absolute value of the current in the bridge rectifier, or essentially, I2. Now, this means that D1 and D3, when they conduct current, essentially they conduct only the positive half cycle and they are zero otherwise. And similarly, for D3, D2 and D0, we'll find that they conduct during the negative half cycle and they are zero otherwise. And so what is the DC component of a half wave rectified signal? Well, the DC component is given by the peak value, which is Im, which is given by this one, say call this Im2. So Im2 divided by pi, because it's half wave rectified sine. And therefore, the maximum current, or the DC current that will flow, or the DC component of the current that will flow in any of the diodes, will be Im2 divided by pi, which is equal to square root 2 IRMS 2 divided by pi.